grating. So here are the examples, the grating, diffraction grating you use in a lab, in our lab. So there are many types, can be 80 lines per millimeter, 100 lines per millimeter, 300 and so on. So that day, last week, we discussed with the single slit great diffraction using a single slit. So here got many slit, thousands of slit. Okay, can be hundreds of slit here. So if you use a white light, pass through the diffraction grating, so you will get a rainbow color like this. Example here lah, top here, the rainbow color. If you use not using white light, for example, you use laser. So laser usually consists of monochromatic light. Monochromatic means the light has one wavelength. For example, the green color here and the red color. Okay, top here you can see. Okay, so next. Okay, that day we discussed for a single slit. Okay, this is single slit. So we derive the equation A sin theta equals to lambda. So we use here A per 2. Then the angle here is equals to half lambda for the dark fringe here. So we get A sin theta equals to lambda. And for the Y separation, the distance, or the width of the bright central bright maximum, okay, we get Y equals to lambda L per A. Okay, this is last week we discussed. Okay, for diffraction grating, we use the same method. Okay, this one is the diffraction grating. So we use D instead of A. Okay, so D sin theta you equate to M lambda for the first order bright fringe to the second bright fringe is the order is M equals to 1. So for the central maxima, M is 0. So the distance Y between them, you can equate these two first. D sin theta equals to M lambda. Then you substitute into the sin theta equals to tangent theta, because theta is for a very small angle. So you can equate them. So you use tangent is Y per L. L is D lah, distance. In the previous lesson, we use D. Okay, capital letter D. So Y per L or Y per D. So you get distance YM. This is distance between two bright fringe. Okay, so the central maxima and the second order M equals to 1. So we equals to M lambda L per D. Okay. Okay, this is supposed to be okay, correct. So D is distance between the two slits. Okay. So same thing lah for both more than one slit. So you use D sin theta equals to M lambda. Okay, you use this equation. So I repeat, M is the number of order. Okay, M start from 0, 1, 2, 3 and so on. And the lambda is the wavelength of the light. Theta is the angle between maxima and central maximum. And then the D is distance between grating slits. Okay, so distance between grating slits in meter. Okay, so the difference between interference and diffractions is for interference is due to the superposition of two different wave trains coming from coherent sources, whereas for diffraction is due to the superposition of secondary wavelets from the different parts of the same wavefronts. So I've shown you last week using Huygens Huygens rule. Okay. So second difference is fringe width is generally constant, but for diffraction the fringe are varying. Okay. For the interference, all the maxima have the same intensity. Okay, like the example given in the picture below. So all the maxima have same intensity, whereas for diffraction, the maxima are of varying intensities. So maxima means the bright fringe here. So middle has the largest intensity. So at M1, 2 and so on, so the intensity decreases. Okay, you can see from the two compare between these two pattern, fringe pattern or interference pattern. Okay, then for the fourth difference, there is a good contrast between the maxima and minima, whereas for the diffraction, there is a poor contrast between the maxima and minima. So the contrast between these two, dark and bright fringe can be differentiated clearly, whereas for diffraction, okay, it's poor contrast, okay, between the two of them. Okay, so these are the differences between interference and diffraction. Okay. Okay, next we go to the example. Okay, example on diffraction grating. So monochromatic light from a helium neon laser. So the wavelength is given 632.8 nanometer, shines at a right angle to the surface of a diffraction grating that contains 150,500 line per meter. So find the angles at which one could observe the first and second order maxima. Okay. Okay, so this is given in the question. So lambda is 632.8 nanometer. So convert to meter. Then D is this is not D, this is 150,500 lines per meter. So for D, separation between two slit is 1 divided by 150,500. So this is for one distance between the two slit. Okay. So for 1 meter, this is number of line. So for one line, so you divide it by 150,500 line. Okay, so you get, so we are going to determine theta 1 and theta 2. Okay, so angles at first and second order maxima, so we rename as theta 1 and theta 2. So we use the formula d sine theta equals to m lambda. Okay, d sine theta for m lambda. So m is 1 and m is 2. So we calculate for m1 first. So for m1, we get theta equals to 5.465 degrees. Okay, so for m2, so we get 10.98 degrees. So using the same formula. Okay, so m is 1. Then the d is 1 per this one, okay, times the lambda. Okay, so this is the first example. For the second example, you substitute m equals to 2. Okay, next, second example. Okay, monochromatic light shines at the surface of a diffraction grating with 5.0 times 10 to the power of 3 lines per centimeter. So the first order maximum is observed at a 15 degrees angle. So find the wavelength. So this question wants to find wavelength. Okay, so given that D, so 1 per 5 times 10 to the power of 3. Okay, so to determine the D, separation between the two slit. And then theta is given 50 degrees. Okay, so for the first order, M is 1. So we use d sine theta equals to m lambda. Okay, then substitute the d here. And then the angle is we are going to find theta, theta is given at 15 degrees. And then sine 15, and then we are going to determine the lambda. M is 1. Okay, so you cross multiply here, so you get lambda 5.2 times 10 to the power of negative 7 meter. Okay. Yeah, any problem with the second question? Okay, no, Okay, next example is a diffraction grating with 600 lines per millimeter is illuminated normally with a monochromatic light of wavelength 589 nanometer. So we are going to calculate the angles of the first order and second order maximum lines from the zero order maximum line. Okay, this example given already in the previous slide. But the second one, to determine the number of orders that can be observed. Okay, number of orders. So this means to determine M. So we do first A, even though we've discussed in the previous slide. Okay, the solution, lambda is given 589 nanometer. Okay, convert to meter, and then N also given 600 lines per millimeter. So you convert to D. D is 1 per 600. Okay, and be careful also, this is per millimeter. So you must convert to meter. Okay, okay, so you substitute into the equation here. D sin theta equals to M lambda. Okay, so M for one order, M1, and then M equals to 2. Okay, some books use N. Okay, so you substitute M equals to 1 and M equals to 2. So for the A question, first order N equals to 1, so you get theta 20.7 degrees. Okay, for the second order, this one is typing error, second order. So M equals to 2, so you substitute 2 into here. And then don't forget 1 per 600, so cross multiply becomes 600 lah. So you substitute the lambda, and this one is for millimeter, so you convert to meter. Okay, so 1 per 600 cross multiply becomes 600 per 1. Okay, be careful with the unit when solve this type of question. So you get theta to 45 degrees. Okay, so any question for A? No, Okay, then we go to the B, Okay, B, the number of orders that can be observed. So the number of orders that can be observed, so you use also same formula, D sin theta equals to M lambda. So cross multiply becomes M lambda per D. Okay, so for number of orders, we can substitute theta equals to 90 degrees. Because if angle is 90 degrees, cannot be shown already in the screen. So theta equals to 90 degrees, substitute into here. So you'll get sin 90 degrees equals to M lambda per D. Okay, then substitute M order for 1 and lambda. Sin theta is 1, sorry, sin 90 degrees is 1. So lambda is D per where? N is D per lambda. Okay, cross multiply. So you get this one, D per lambda. So for N number, we substitute as N lambda. N lambda. So, sorry, D is 1 per N. Okay, D is 1 per 600. Okay, so you substitute into here. And then another one is, and must be careful with the millimeter. Okay, millimeter, so convert to meter. Okay, now substitute all already into the equation. So you get N is 2.8. So the number of order cannot be in a decimal number, cannot be in decimal number. So you must round it off, but you cannot round it off to 3 because if larger than 2.8 is more than 90 degrees. Okay, so must be very careful. So for diffraction grating, to find the number of orders, you must get the lower number than 2.8. So that means the lower integer, lower integer than 2.8 is 2. Okay, don't round off to 3. I repeat again, don't round off to 3. Because if you round off to 3, so that means the angle is larger than 90 degrees. Okay, so it's not possible. Okay, so N equals to 0 is the correct answer for the number of orders. Okay, for more example, you on concerning on the number of orders, you can refer to your textbook. Okay, any question on this one? On this question? So this is the common mistake students make. They round it off or to 3, or either they leave their answer as 2.8. Okay, this is common mistake students makes every year. So be careful. Okay, so if no problem, we go to the next question. Sure, no problem. Okay, so we go to next question. a diffraction experiments is carried out with a grating. Okay, so we use light from a red laser, lambda equals to 630 nanometer. So diffraction fringe are separated by H equals to 0.15 meter. Or in the previous slide, we use a Y instead of H, same meaning, okay? H or Y, okay? The distance between the fringe is 0.15 meter. And then the distance W from the grating. So in the previous slide, we use D, okay? So in this question, it used W. So it's 2 meter from the grating. So find the spacing D between slits in the grating. So the question can ask you D also, to determine the D spacing between the slits. Okay, so the solution. So this is to imagine how it looks like, okay? The questions ask for this D, the separation grade, the spacing D between the grating. So the angle theta here, so H, the height of the separation between the fringe, then the D or W given in this question from the grating to the screen, okay? Okay, then we use D sine theta equals to M lambda. Okay, so M for one order, the first order, you can choose any order, but the easier one is the M1 because the separation between them is all the same, okay? All the same, H. Here also H, here also H, here also H. So we choose for M1, from M0 to M1. Then we substitute into the equation, but we don't know theta, so we need to find theta first. To find theta, we can use tangent theta equals to H per distance here. Okay, so H per W. So we substitute H 0.15 meter, and then the D or distance between the grating and the screen is 2 meter. So you get 0.075. So the answer theta is 4.3 degrees. Okay, in radian 0.075 radian. So purposely I show here in radian because for a very small angle, okay, the theta in radian is equals to 4.3 degrees if you substitute into here. So we try to substitute both theta in radian and in degrees, what we get. So we try substitute D equals to lambda per sine theta, where sine theta we use radian, 0.075. So you get 8.4 times 10 to the power of negative 6 meter. So if you substitute here sine 4.3 degrees, okay, you get the same answer. Okay, you try on your own. So even though you divide it by in radian or you use 4.3 degrees, sine 4.3 degrees here, you get same answer. 8.4 times 10 to the power of negative 6 meter.